Here we go, friends. So we're on 2C.12. We are halfway through this unit. So this is unit 2C, and this is our fourth section in unit 2C. Um, and so log function manipulation. We're going to be applying the properties of logs to evaluate expressions and graph functions. The properties of logs are we've learned before. We're going to use the properties of exponents and logs to simplify and evaluate expressions, and then we're going to recognize the graphic translation. So this should go fairly quickly because it should be a build on of previously taught material. Okay. There's broken into two parts. So we're going to start with part A. So part A we have here is, do you remember these log properties? Do they look familiar? Yeah. Okay. So we have our product property. Our product property is stating that when you have two arguments that are being multiplied, you can separate them into two separate log problems that are being added. Yeah. Same applies to natural log. The quotient property is when you have an argument, two arguments that are being divided, you can separate them into two log problems that are being subtracted. Cool. And then our third property is power property. And with our power property, hey. All right. And then last is our power property. The power property is stating that when you have a power on an argument, that power on the argument can also be the coefficient of the log. Okay. The power on the argument can also be the coefficient of the log. So these are our three properties for log and natural log: the product, quotient, and power. Do we remember these? Yeah. Okay. And they correlate to our exponent rules, right? Following those things. So let's apply some of these logs. So here we have, it says to expand. If we're expanding, that means we're trying to create as many individual log terms as possible, okay? So if I wanted to expand, I have here log of 8xy to the fourth, okay? So when I expand this, I'm going to be using which property? I'm going to use the product property. So this is product, or not. Yep, there we go. So this is going to be product property. Product property says that I can take each factor and write it as its own log term. Does that make sense? So I'm going to take each factor, 8xy to the fourth, and write it as its own log term. So that's going to give me log of 8 plus log of x plus log of y to the fourth. Okay. I then can also apply the power property to the 4, but now that we're in pre-cal, we're also going to apply it to where we can break down a value into its factored form. Well, factored form. So 8 has another way to be represented. Could 8 be represented in terms of a power? Yeah, so 8 can be represented in terms of a power. So we can manipulate this to be 2 to the third. Agree? Because 2 times 2 times 2 is 8. So therefore, when I use the power property, I also can apply it to the log of 8. The log of 8 becomes 3 log of 2, and then plus log x plus, and then the power of y becomes its coefficient, 4 log y. And that would be the simplified and expanded form. Okay, in Algebra 2, we didn't really focus so much on the simplified. We just wanted to expand, right? And pre-cal, take it up a notch. Can you simplify before you expand? How do you feel? Not terrible? Not too bad. I'll take it. All right, so now let's look at this natural log. So we have the natural log of the square root of x squared plus 5. So the first thing I'm going to do is rewrite this in terms of power. So when I rewrite this in terms of a power, it's going to become the natural log, parentheses, x squared plus 5 to the 1/2. Yes? Over x. If I'm taking the square root of something, that means it's to the half power. Okay? So looking here, I have arguments that are being divided. Because I have arguments that are being divided, that means I'm going to use what property? The quotient. Okay, because I have arguments that are being divided, I'm going to be using the quotient. The quotient is your numerator, the log of your numerator minus the log of your denominator. So in this sense, in this case, we have natural log of x squared plus 5 to the 1/2 minus the natural log of x. After I applied the quotient property, I still have a power, and that power can be moved because of the power property. So the power property leaves me with 1/2 natural log of x squared plus 5 minus natural log of x. And that is my expanded answer. And I didn't box this one, so let me box it really quick. Okay, how do we feel about expanding? A lot of mistakes happen with x squared plus 5, but these aren't factors in an argument. These are terms, right? And the product rule only applies if they are factors. The factors then can become the sum of the logs. Okay? Keyword are factors, and these are terms, not factors. Terms you add, factors we multiply, right? Good? All right, let's go reverse. Okay? Can we condense? Yes. When you're condensing, you're going to start with power first. So when you condense, you start with the power property first. After you do the power property, you then decide, is it going to be quotient or product, working it from left to right? Does that make sense? So we start with power, and then we determine whether it's quotient or product, working it from left to right. Okay? So the first thing we're going to do is our power. So power tells me that natural log of x to the 5th is going to stay natural log x to the 5th because it was never moved. However, this one is going to be moved. Make sense? So now we're left with minus log of xy squared. Okay? Now, there's only one operation here, which is lucky for us. So because there's only one operation, that this is going to lead us to what? Minus leads us to quotient. Bless you. So minus is going to lead us to quotient. So that means we now have the natural log of x to the 5th over x squared times y squared. Did I mess up anyone with that step? Okay. That's because the power applies to each factor, right? So you get a 2, you get a 2, and that's why they became that. Now, this is using the rules, but is it simplified? No. Why is it not simplified? The x to the 5th and the x squared can be simplified. Yes. And it turns into x cubed. So this actually equals the natural log of x to the 3rd over y squared. All right. Between these two examples, working backwards, expanding, I now want you to try B. If you don't feel confident in doing B in the notes, then do it on a separate piece of paper or do it in a pencil. But I want you to try and condense B and simplify it. Condense and simplify. All right, so remember, we're going to do our power rule first, right? That's a P. Go with it. So you're going to become a power, and you're going to become a power. So we have the natural log of x to the 3rd, y to the 3rd power, plus natural log of yz squared. Yes? All All right, after we do that, now we're going to decide what's going to take place. If you would like to distribute before, that is A-okay. So I'm going to go ahead and distribute. Is that cool? X to the ninth, Y to the third, plus natural log of Y squared, and Z to the fourth. Okay, so now I only have one operation taking place, and it is addition, which tells me that this is going to be a product. So combining them, it's natural log, and it's the product. So that means I'm taking this argument and multiplying it times that argument. So we have x to the ninth, y to the third, times y to the z, z to the fourth. And I'm going to clean this up because that is not simplified. Y to the third times y squared is y to the third times y squared is y to the fifth, z to the fourth. And there you go. Questions, comments, concerns? Not this moment. All right. Yes. Okay. So yes, we're talking about exponentials, but you already meant logs, but you have the exponent rules in your head, right? You should know these from Algebra 1 and Algebra 2. The exponent rules still exist. Okay. All right. Let's talk about change of base. Now, change of base isn't necessary for calculating anymore. It is necessary for when you're simplifying. Does that make sense? Okay, that's because our calculators have been upgraded and we can now put whatever base we want for a log in a calculator, correct? So at this point, change base is not for calculation, it is for simplifying. Make sense? All right. So here, if you have base A, to change the base, what you're doing is you're going to just choose a base. Doesn't matter what the base is, but they just whatever base you need them to have alike. And you're going to take the argument, so the log of the argument over the log of the base. Log of the argument over the log of the base. Whether it's base 10 or base E, which is natural log. Doesn't matter. It is the log of the base, the log of the argument over the log of the base. Log of the argument over the log of the base. And they are equivalent forms. Okay? So, for example, this would be useful if I had an exponent as a base and I need to separate it from its argument. Does that make sense? I can then separate them by creating change of base. All right. But evaluating here by using change of base simply would be if I couldn't type this in a calculator. Let's say I was using my phone calculator, a handheld calculator, right? Not a fully handheld, but my phone calculator. I can't type log base 313 in the calculator. However, I can type log of the argument divided by log of the base in my calculator. So I'm going to pull up a standard calculator. Standard calculator. Here it is. And now I can do log of 13 divided by log of 3. However, I couldn't do log base 3 of 13. Does that make sense? But I can type in separately and still get the result. So I get approximately. What if it's not available, Hudson? Okay, cool. But we're understanding the point, right? Now, yes, we have our calculators. Yes, our calculators are updated. Yes, if I press alpha window, I can do log base change. I understand that. But what if I couldn't? Is the goal here or the idea. Does that make sense? On the what? No, we cannot. Okay. Nice try though. Log of 13 divided by log of 3. And oh my gosh, it's still going to be the same. Okay. That's the whole purpose of this. Now, just to make sure you understand, this was really a big deal back when calculators didn't have that upgraded feature. I get it. Okay. We're still in the 2000s. Just want to point that out. But anyways, you get what I'm saying. So easy enough. So just make sure if and when you need this tool, we can do it. So again, it's the log of the argument, which is 10 over the log of the base. Easy enough. Log of the argument over the log of the base. And you can either write it as natural log. If you don't want to do log, you can also do natural log. It's still going to do the same thing. Hello, Lupe. You can also have natural log of 13 over natural log of 3. They're going to be the exact same thing. That's how change of base works. All right. Questions about change of base? I really don't have anything else to say about it. Okay, just to double check our no need for calculator. What is this answer? What's the answer? Huh? What's the answer? You just took a quiz over this. Yes. What happened on the quiz? Question then. That's the scary part that you asked.
I need to open people.
That's what I'm saying.
I need to open days.
Yes, exactly. So this would be asking you 1/2 to what power would equal 10. You used a calculator, Hudson. I see it in your hand. It's in your hand. 1/2 to what power would give me? It would be -1 because -1 would take the 2 out of the denominator. So C, you shouldn't actually need a calculator or change a base for. Right. Yeah. Mm-hmm. Yeah. All right, let's go on. The last part of part A is applying this to, graphing or real world situations. Here we come. All right, when graphing log functions in the form of y equals log base b, k times x, we can show that the product property can be separated into log base b of k plus log base b of x is equivalent to a vertical translation, which makes sense. I promise you. So for example, we're going to graph log base 2 of 4x, right? Log base 2 of 4x is in this form, like your standard form. We know that looking at this is a horizontal dilation, right? By what? Translations, I told you, you got to live and breathe translations. They come up the entire year. X's are liars. So it's not by a factor of 4, it's by a factor of 1/4. So this is a, this would, in the way we're reading it, it's a horizontal dilation by a factor of 1/4. Agree? Yes? Because our x's are liars. So even though we want to be like, oh, that's multiplication, x is lie. That's why they should stay x's, okay? All right. So we're going to look at this. We're going to use technology to show you that logs are beautiful things. Not only is this can be viewed as a horizontal dilation by a factor of 4, but it also can be viewed as a vertical translation. And we're going to talk about what that vertical translation looks like. Got it? Let me pull up Sylvie, homegirl. If you have either your Desmos or your handheld, whichever, pick your poison. Here is mine, because I'm loyal. The rest of y'all. Second plus 7, 1, 2. We're going to reset Sylvie. Okay, so I'm going to first graph log base 2 for x. So I go to y equals. Again, how do I get change of base? What's the shortcut that has been added to our beautiful calculators? Alpha window. We're going to go to alpha window. And we're going to press 5. And now I can type in freely log base 2 for x. Okay. so that I can get accurate points to try to sketch my little graph, because we know I need points to connect things. Otherwise, I struggle. I'm going to go look at the table so that I can have, I'm going to go second graph and pull up my points. All right. Why is there an error at 0? What makes it stop? What are those? The limit. What? Okay. Thank you. That was the word we were looking for. There is a vertical asymptote here at x equals 0. So that's where we are no-go zone, right? All right. So I'm going to plot my whole numbers. 1, 2. So I go to 1, go to 2. I'm going to go to 2, go to 3. I'm going to go 4, 4. And I can get in there. Can I get in 8, 5? I can't get in 8, 5. All right. So again, even though Miss Jones has points, we're going to still pretend that this is the best exponential log function you've ever seen. Guys, I think that is legitimately probably one of my best drawn while we're pretending. Like, for real. This is serious.
The best.
The best. I'm proud of myself. All right. And we're going to label it G X. Okay. So now we just reviewed our log expanding properties, right? If I wanted to expand log base 2 4x, what does that expand to? Let's do that. Which property am I using? Flip over if you don't remember. Just flip your paper over. I want to expand it. There we go. We're going to use product property to expand. I asked y'all. Y'all couldn't tell me, so I tried to give you hints. You just had to read, but no one wanted to. Okay? So we're going to expand. So right now we're at log base 2 of 4x. When I expand this, it becomes log base 2 of 4 plus log base 2 of x. Now what I want you to do is I want you to graph this and tell me what happens. You know, just for giggles. Just do it. Tell me what happens. Just for a little giggles. On the calculator. No, on your hand. Yes. All right. So in your Y2, or if you're using Desmos, graph our expansion and tell me what happens. Jacob, what happened over there? What happened? It's what?
That's impossible.
That's it. That's crazy. That's so crazy. Let me go see. So you say I'm going to get the same thing? Let's see. 4. I'm going to type it in. Shh, Hudson, go along with it. All right. So I'm going to hit graph. Okay. So there's my Y1. Oh my gosh. It's changing colors. That's crazy. It's the same thing. So our conclusion here is what? A horizontal dilation is the same thing as a what? It's going to be a same thing as a vertical translation. Okay. That's because of that product property. That product property is going to make it the same thing. Now we're going to clean this up so that you can see what this would look like. And someone tell me, what is log base 2 to the 4? And we just had a quiz, so please don't tell me you don't know this. What is log base 2 of 4? 2. Thank you. Thank you very much. So 2 plus log 2 base x. So again, we can see that that's a vertical translation 2 units up. Yes? All right. So we have a vertical translation 2 units. Okay, so I'm going to go ahead and graph my f of x, which is my parent function, so that we can see that all this is true. So f of x, and it says make sure you graph both f of x and g of x. Right now, we only have what graph? Our g of x. So we're going to graph our f of x, and I need to be able to change my pen color. But I don't know how it's going to, this little bar won't go away. Not f of x. There we go. Okay. So if I have log base 2 of x, just log base 2 of x, my f of x isn't the same. It's my parent function. We're going to go over here. I'm going to go to y equal. Is it okay if I delete this one? No one's going to be like, oh, Miss, what happened? Out the window. And we're going to 2x. And again, I'm going to go to the table so I can see my values. So I'm looking at the parent function. The parent function, again, still has the error because there's the vertical asymptote. But I'm going to graph at 1. I'm at 1, 0. I swear I changed the color of this to red. Or at least I told myself to. 1, 0, and then 2's at 1, and then 4's at, and then 8's at. Thank you. And again, I'm going to try real hard again because I'm pretty proud of myself right now. If I can do this, I can do anything. Cool. All right. So do we see how that horizontal dilation is also that vertical translation? Can we make that connection permanent? Yes. Mission accomplished. All right. So in your own words, this is practicing writing and explaining yourself. You're going to describe the change in the output values over the equal values. So how is it changing? So when I'm asking that, I'm asking as x increases by what this is taking place, our y values are doing this. So looking at them as our x values are doing this, our y values are doing blah, 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 blah. But you're telling me exactly. So remember how we analyzed our tables? Yesterday, well, 2 days ago, as your x's increase by what did your y's do? That's what I'm asking you to do. So describing g of x. Tying back into us being able to describe our tables or our functions from 2C.10. And again, it was just on the last two tables. How did they change? The increase, decrease, or the y's or the x's? Who was doing what? To what?
After you're done with this, can you go back to example number 3?
Can I do it towards the end? Because we have part B to do. Okay. That's okay. Yeah. I asked you to describe the change in the output for a g of x. So what happened? You're writing in your own words. I'm not going to write the words for you. You're learning to write your own words to describe what's happening. Yes. No, I'm going to just stare at you. No. Yes. But I want you to try and write it, guys, because you have to be able to justify, especially on your FRQs. That's where some of your points are going to come from, is explaining yourself. When you're asked to explain, you need to be able to explain. Now, my words may not be your words, and that is A-O-K, right? Now, there's two ways you could have described this. The first way would be describing what happens to your input, which is using the dilation, right? So using the dilation is describing how your X values are affected, but it says how your output, how are your Y values affected. And because it says output, we would be talking about the translation, like what happened with our Y's, okay? So in this case, for G of X, as our x increases, that says increases by 1 unit. So that was the steady increase. Our x values are going up, right? By 1 unit, the values did what? What did my output do?
The output increased by 2. Um,
Well, compared to the g of x. So g of x from here, what happened?
decreased
The y values increased, right? And that's by how much? By 2. Did you say 2?
Yeah, earlier I said they increased by 2.
Oh, I didn't hear that. My bad. I heard in my brain, your words did not process. So, yes, you're right. I didn't process what you said. It's me. I'm the problem from the parent. Oh, my y. There you go. All right. So, we're going to